Hi everyone, my name is Brian and I'm a PhD student in the School of Computer Science in NUS. And today I'm going to introduce our paper called Confidence Elicitation, a new attack vector for large language models, where we basically introduce the concept of confidence elicitation attacks. Now, our work builds directly on top of previous work on the matter of uncertainty estimation and adversarial attacks on LLMs. Our motivation is that the closed source nature of LLMs is often used to argue against white bots and gray bots attacks on NLP models. But as we all know, LLMs can do free-form generations, which means you have an input set of tokens and an output set of tokens. So our question is, can we use some sort of emergent ability of LLMs to craft adversarial perturbations? And we believe we can, and to this end, we introduce confidence elicitation attacks. So the first two blocks of our frameworks comes from previous work where they basically explore how well LLMs can express their uncertainty verbally. And our novel component, which is the last block, the third block, is basically we use the output values from this uncertainty quantification to close the feedback loop and perform black box optimization. So the threat model is as following. We assume a fixed model, fixed prompt strategy, and elicitation type. We then assume that we have an aggregator that works and takes the output from the LLM and can result in one final answer and one confidence value. We have full access to the input text, so we can change it and then pass it to the prompt and model. So our setup for the proof of concept is as following. We choose k-guess prompting strategy with a verbalized confidence elicitation type, and then a Dirichlet aggregator where we basically build a prior, and then we sample from this prior the answer and the confidence. So to give you an example of how this works, in the top left corner in green, we have an example such as, did Aristotle use a laptop? And we ask the model for k guesses. So we use the k guesses prompting strategy. And the answer could be something like false, false with very high confidence. And then maybe the model gets it wrong and outputs true, but it's very low confidence. So after we build the Dirichlet prior and we sample from it, then the answer will be correct and be something like false with a very high confidence of 0.8. Now we can use this output value of 0.8 to basically craft a perturbation denoted in step 3 as delta 1, and it's modeled after a word substitution. For example, we go from the word use to utilize, and after we do inference again, we will see that the confidence maybe drops. And we assume that as the confidence drops, the likelihood of misclassification increases. And then we can keep doing these perturbations until the misgeneration happens or a misclassification happens, and we achieve a high confidence on this misclassification or misgeneration. So previous works in Blackboard's baselines work by overperturbing a sample by maybe changing all words. And then they see that one of these samples is adversarial, and then they try to increase the quality by maybe changing some of the words to the original ones, and they keep prompting the model to make sure that it's still adversarial. Our technique is more direct, so we change just one word at a time, and as we're minimizing the confidence, we increase the likelihood of misclassification. In our results, we first show that the models are calibrated, and we achieve 5 to 15 point deviation in expected calibration error, which results in a calibration curve that is very close to the optimal diagonal line, allowing us to extract a meaningful feedback signal to perform our black box optimization. This leads us to achieve a higher attack success rate than other baselines. And because it's more direct, the optimization process, we also are able to achieve this by querying the model less times. So in conclusion, we introduce a novel attack vector, which can be used as an effective feedback signal for black box optimization. And our attack achieves state-of-the-art attack performance on word-level, hard-level attack on LLMs. Check out our code and paper. Thank you so much for listening.